Okay, class, in lesson 2.5, we are going to have two main goals. We're going to be introducing you to the greatest integer function, which is another one of our parent functions. So it's going to kind of go with that library of parent functions we talked about before. And then in the second half of this lesson 2.5, we're also going to be looking at how to perform some transformations on all of these parent functions. So in this video, I want to simply focus on this greatest integer function. And again, we're going to add that to that library of parent functions that we have. Now let's start with what is an integer. By definition, remember that an integer is the set of all whole numbers and their opposites. So when we talk about integers, we are basically excluding any fractions and decimals, since those don't fall into the category of whole numbers and their opposites. So integers are basic 1, 2, 3, 0, -1, -2, -3, and of course on and on and on. Now, when we talk about the greatest integer function, we're basically talking about what is the greatest integer that is going to fall, I guess, kind of in a number, okay? So before we look at what that means, I do want to point out that there are two different ways that you might see the greatest integer function written. So we could see it look like one of these two. No matter which of these we see, we still read it as the greatest integer less than or equal to x. And that's kind of the key, less than or equal to x. So what does this mean? If I ask you to find the greatest integer, and I give you a number 3.2. Now, first of all, I do want you to notice that this is not the same as absolute value. Excuse me, these look more like brackets. Same thing you would see almost in a matrices. Now, what does it mean to find the greatest integer less than or equal to 3.2? If you think about it on a number line, 1, 2, 3, 4, 3.2 would fall right about there. So what is the largest integer before we hit 3.2? Well, that largest integer is going to have to be this 3. So the greatest integer of 3.2 is actually 3. And if I was to ask you for the greatest integer of 1.7, okay, well, again, think on a number line. Here's 1, here's 2, 1.7 falls right about there. What is the largest integer before we get to 1.7? Again, that's going to be 1. So the greatest integer here is 1. Now, what you might be noticing is that we are essentially rounding down, right? We're rounding it down to 3, and we're rounding the 1.7 down to the 1. So you can kind of think of greatest integer as rounding down. But you do have to be a little careful. It does become a bit tricky when we start asking about negative numbers. So if I wanted to know the greatest integer of -2.3, well, on a number line, -1, -2, -3, -2.3 falls somewhere in here. If we're sticking with rounding down, then the greatest integer within this -2.3 is still this. Remember that as it appears that it's getting larger, but we know that the numbers are actually getting smaller as we go to the left on a number line. So here, we're looking at a -3. So the first thing we want to be able to do is evaluate the greatest integer function. So kind of like what we saw before, if I asked you to, if I gave you the greatest integer function, and I said I wanted you to find f of 1.2. What I'm asking then is, I'm asking you to plug in 1.2 here. So I want to know what is the greatest integer of 1.2. Again, on a number line, 1.2 falls here. The greatest integer before 1.2 is 1. Okay? If your number that you're plugging in is an integer, the greatest integer is still going to be 3 at this point. So if you think about, think about on a number line between 3 and 4. If I have 3.1, the greatest integer of 3.1 is going to be 3. If I have 3.3, the greatest integer of 3.3, still going to be 3. If I have 3.9, the greatest integer of 3.9 is still going to be 3. If I ask you for 4, the greatest integer of 4, so the largest integer in 4 is in fact 4. So when you kind of look at it like that, I'm going to put that first one up here too. The greatest integer within 3 is 3. So as you can see, everything here rounds down to 3. Once you hit 4, it's like you're starting almost a new part of the graph. Okay? The greatest integer of 5.9 rounds down to 5. Remember those negatives? I'm going to skip to this one. The greatest integer of negative 9.9. Okay, remember your number line. Here's negative 8, here's negative 9, here's negative 10. Well, negative 9.9 is here, and that's going to round down to negative 10. So the reason we need to be able to evaluate the greatest integer function is because that's going to help us to actually develop what that parent graph looks like. Okay, so now if I asked you to graph the greatest integer function, and keep in mind that this graph can look a couple of different ways. So you could see, I'm sorry, not the graph, the equation could look like this, or the equation could just say integer x. They mean the same thing. In order to kind of see what this graph looks like, I'm going to recommend that we make, at least this first time, just a really long table and we plot some points. So for example, what if I plugged in 0? Well, what is the greatest integer of 0 is in fact 0. Remember that the largest integer up to 0 is itself. Okay, well what if I plugged in 0.2? Well, if I find the greatest integer of 0.2, that's actually going to round back down to 0 again. 0.5, that's going to round back down to 0. 0.9, that's going to round back down to 0. As soon as I plug in 1, the greatest integer in 1 is itself. If I do 1.2, that rounds back down to 1. 1.5 rounds back down to 1. 1.9 rounds back down to 1. You notice the pattern here, right? If I plug in 2, the greatest integer in 2 is 2. And it kind of keeps going. 2.1 rounds to 2. 2.9 rounds to 2. Greatest integer in 3 is 3. And it kind of continues. Okay, so now how do we plot this? Well, at 0, 0, we're obviously right here. At 0.2, we're still on this line. At 0.5, we're still here. At 0.9, we're still here. But all of a sudden, when we get to 1, we jump up to right there. And then 1.2, we're here, 1.5, 1.9. And then as soon as we get to 2, we jump up to here. And then we've got 2.1, 2.5, 2.9. As soon as we get to 3, we jump up to here. So how are we going to show this? We show this by showing that everything along here stays at a y value of 0. But as soon as we get to 1, so I'm going to use an open circle there, because once I plug in 1, I'm no longer going to get a value of 0. It's everything up to 1. Once I plug in 1, then I jump up in the graph, and now all of these have the same y value until I get to that point. And then again, it jumps up. All of these have the same y value until I get to this point, and then it just keeps doing that. It jumps up again, and it's going to keep going. What you want to notice, and it will technically, it'll go the other direction too. So at -1, okay, I would have all of these would have a y value of -1 until I get here, and then it popped up to 0 again. So this graph will continue with these little steps all over the place. That's why this greatest integer function is sometimes also called the step function, because it does actually look like a staircase, like you're hopping up a set of stairs. You'll also notice that technically a step function or a greatest integer function is actually a type of piecewise graph. It's like graphing multiple little pieces that are all little mini horizontal lines, okay? We can see that this graph is not continuous since we're obviously taking breaks as we jump across. Now, We're going to be spending some time talking about transformations, but without even, performing the transformations or reviewing maybe what those look like, I could still have you graph an integer function with maybe a simple transformation along with it. So if I asked you to graph the greatest integer of the greatest integer of x plus 1. Well, we could do kind of the same thing, okay? Plug in some different values for x. If I plug in 0, then I would do the greatest integer of 0 plus 1. Well, that would be 0 plus 1, I'd be left with 1. If I plugged in 0.5, that would be the greatest integer of 0.5 plus 1. Well, the greatest integer of 0.5 is still 0, so that would still be 0 plus 1 or 1. Okay, if I jumped up and plugged in 1, well, the greatest integer of 1 plus 1, that's going to give me 2. If I plugged in, let's say, a 1.9, well, the greatest integer of 1.9 is still 1 plus 1, still 2. If I plug in 2, the greatest integer of 2 is 2 plus 1. Now I'm at 3. If I plugged in 2.4, the greatest integer of 2.4 is still 2 plus 1, still 3, and etc., etc. So when we went to plot these, this time when x is 0, we're going to be up here at 1. When x is 1/2, we're still up here at 1. And keep in mind that just like with all of our step functions, I should actually do a different color here. So basically all of these numbers until I get to 1 are all going to have that same y value of 1. Once I get to 1, I actually jump up to 2. And then all of these numbers until I get to 2 have the same y value. And then once I get to 2, I jump up to 3, and all of these numbers have the same, and it just keeps going. So if you compare this graph to the original one, remember the parent function was just f of x equals f of x equals greatest integer of x. That was the parent function. And the parent function that we saw up here, it's the same graph, except that it's shifted. In this function, this whole graph shifted, let me do this here, this whole graph shifted up 1. And that will bring us into our review of performing all of these different transformations on graphs. That will be in our next video.